Good afternoon, everyone. This is Dr. Coker, and today I will be talking about experiment 4, adsorption. Here's a brief outline of the presentation. We'll go through the background on adsorption theory, then I'll go through the problem statement, what is required in the lab, a short analysis of the laboratory data, and some safety precautions. So this lab, actually, we handle a lot of chemicals, therefore we have to be very, very careful, and we'll talk about all of those chemicals that we're going to look at, and they're highly flammable. Some supplemental reading. I recommend, and I highly recommend, that you get a copy of Separation Process Principles from the library, or you may already have a copy, and go through chapter 15 titled Adsorption, Ion Exchange, and Chromatography. Now, this chapter is a very good background for what the experiment is about, and it also explains very clearly how you can get your experimental data. So you should actually go and read this chapter. Additionally, I recommend reviewing your CHBE 390 notes, where we talk about adsorption and the Langmuir isotherm, as well as your CHBE 411 and 412 notes, where we talk about heat of reaction, as well as CHBE 301. Okay, so you may have to go back and look at some of your notes throughout the past few years. So the big question is, what is adsorption? So adsorption is a process in which molecules, atoms, or ions in a gas or liquid diffuse to the surface of a solid, where they bond with the solid and are held on by weak intermolecular forces. And these weak intermolecular forces are often called van der Waals forces. However, if you have chemisorption, you can have stronger forces. So what we're concerned with is more physisorption, which is weaker van der Waals forces. Now, some important nomenclature. The adsorbed solutes are referred to as adsorbate. So this is my adsorbate. And in this experiment, your adsorbate will be either benzene, toluene, or cumene. And the solid material is called your adsorbent. And in this case, for this lab, your adsorbent is molecular sieve 13X. Adsorption is mainly a surface phenomenon, and like I mentioned in the previous slide, you can have chemisorption, where the molecules are held onto the surface by chemical bonds, and those chemical bonds could be hydrogen bonds, they could be covalent bonds, and then the other one is physisorption. So in this lab, we're actually looking mainly at physisorption, where you have weak van der Waals forces. Now, depending on your adsorbent and your adsorbate material, if you look at a curve that will plot the concentration or the mass of adsorbate over adsorbent versus pressure or concentration, we use concentration if we have a liquid, and we use pressure if we have a gas. If you have a system where you see a monolayer, what you're going to get is something that looks perhaps like saturation kinetics. So it looks very similar to your Michaelis-Menten kinetics. Now, the reason for that is simply that once you have filled in your monolayer with these adsorbate particles, you cannot fill it any further, so it's actually saturated. So this follows what we know as saturation kinetics, okay? Now, if you have a system where you can have multi-layers, what happens is you're going to get some type of S-shaped curve. So this initial part of the curve represents when you have completely filled the first monolayer. And then it goes up subsequently as you're adding more and more layers to the system. And there are several different types of curves, and we'll only talk about 5 of them in the next few slides here. So, as mentioned previously, we have different adsorption isotherms, and the most common ones we see are the following. So type 1 is your monolayer, and this is usually your Langmuir isotherm. And then we have type 2, which is multimolecular. So you may have several different types of molecules adsorbing onto the surface. Type 3 is what we call unrestricted. So you get this hyperbolic type of function right here. So it's also known as a hyperbolic isotherm. Type 4 is what we call multilayer adsorption with capillary condensation. And this one, in some cases, also has a hysteresis effect. So if you're adsorbing or desorbing, you can actually get a slightly different curve because of the hysteresis. And type 5 is capillary condensation, and it's actually a version of both the type 2 and the type 3 curves. And your goal in this lab is to conduct the experiment and figure out what type of a adsorption isotherm you have. And we'll go into detail. There's several other types of adsorption isotherms as well. Some of the commonly observed or reported isotherms are the linear isotherm. So you get this equation right here. And then we have our Langmuir, what we talked about, saturation kinetics. So something that goes up like this. And then we have an exponential type of isotherm. It's called your Freundlich isotherm. So in this lab, after you identify what type of an isotherm you have by simply plotting your adsorption density versus your concentration, you're going to be actually asked to figure out what the constants are. So you have to first identify the type of isotherm, and once you have that identified, you should be able to calculate the constants. Okay? So here's the problem statement. So you're going to determine the type of adsorption isotherm in your system for a mixture of 1-hexene or N-hexane, which are solvents, and an aromatic, benzene, toluene, cumene. So you're going to dissolve benzene, toluene, and cumene into either hexene or N-hexane. Every group will be given a different mixture. And then you will observe the aromatic adsorb onto molecular sieves 13x. And you will conduct this experiment at 3 different temperatures: 20 degrees Celsius, 4 degrees Celsius, and negative 20 degrees Celsius. Once you've identified the type of isotherm, you need to determine the constants for this isotherm. And last but not least, you need to figure out the heat of adsorption. So in the next slide, we'll discuss what the heat of adsorption is. So the heat of adsorption is the amount of energy released when an adsorbate is adsorbed onto an adsorbent. Okay, so what does that mean? You have your adsorbent and then you have your adsorbate. So when your molecule comes and adsorbs onto a solid, it will actually release energy. So it's an exothermic reaction. And quantifying this energy helps us determine the amount of energy that's actually required for us to desorb that material. Okay, so the heat of adsorption, I'm not going to go into any more detail. I'm going to recommend that you review your thermodynamics as well as your CHBE 301 lectures to see how you can actually determine that with the material that we have in the laboratory. So this slide here actually sums up what's required. So you will have solvents 1-hexene and N-hexane, and these will be used to dissolve aromatics such as benzene, toluene, or cumene. Now molecular sieve 13X comes in different shapes. You can see these little tiny balls here. The one in the lab you'll be using are 2 millimeter balls, and I've also seen molecular sieves that are more cylindrical that look like that. Okay, so what you're going to do is you are going to set up several different beakers with different concentrations of your benzene, toluene, or cumene at concentrations that range between 100 parts per million all the way up to 1500 parts per million. So what you're going to do is you're going to add your molecular sieve to the bottom of each one of these beakers, and then you will be adding your solvent, and inside your solvent you're going to be mixing your adsorbate molecules. And you will set these at 3 different temperatures. So 20 degrees Celsius, you can leave them on the bench. For 4 degrees Celsius, you can put them inside the fridge, and -20, you can put them inside the freezer. And you will set all these up on your first day of your experiment, and then you'll come back a week later and do your calculation. So you'll take an aliquot of each sample and run it through your GC, and once you run it through your GC, you can actually plot it. Okay, so what you're going to plot is essentially on the next slide here. So I don't know what type of isotherm. Here I'm just assuming you're going to get a Langmuir isotherm. So what you're going to essentially plot is your grams of adsorbate per gram of adsorbent, and you have your equilibrium concentration. Your system should essentially be at equilibrium when you come back after a week, and then you're going to have your 3 different temperatures. Now, once you've identified the type of isotherm, you can go ahead and find the constants for that isotherm. Now let's go through some safety precautions. Now, the chemicals that we're using are highly flammable, and everything needs to be done underneath a fume hood. You really don't want to be breathing anything in or leaving it out in the lab because there are carcinogens with the materials you're working with. I also recommend that you go through your MSDSs. You have to be wearing nitrile gloves when handling the chemicals. The latex gloves are not going to protect you. Also, try to handle the smallest possible quantities of chemicals. So when you're mixing your dilutions to do your experiment, don't be mixing a huge quantity. So that actually summarizes this experiment.